We're continuing with the 9196 worksheet 2, looking at starting on page 3 here, number 20. Uh, so if we try to determine whether the series will diverge using nth term test, we're going to see that the limit of this rule of sequence will go to 0, so the nth term test is inconclusive. But here we see exponential function, so ratio test is probably a good fit for this. So if we go through ratio test, it's a limit as k approaches infinity for a sub n plus 1 divided by a sub n. So here's representation for a sub n plus 1. Replace each k with k plus 1 and divided by a sub n, and which is the same thing as multiplying by the reciprocal of a sub n. And if we try to simplify this, the 5 to the k and 5 to the k denominator will cancel out, leaving us with just 5. And we have k plus 6 over k plus 5. For k approaches infinity, we simply look at the coefficients of the leading coefficients. We get 1/5. 1/5 is less than 1. Therefore, the series will converge by the ratio test. Number 21, we see that this entire expression can be rewritten as raised to the nth power. So if our entire expression can be raised to the nth power, root test is a good fit usually. So root test just says find the limit as n approaches infinity for the square root or the nth root of this expression. And if we take the nth root of this expression, the n's cancel out. We're left with just 2 squared over n, and limit as n approaches infinity for 2 squared over n will give us 0. And 0 is less than 1, so that's enough to fulfill root test, and so therefore series converge. 22, if we see something like this here, we can go through the nth term test for divergence, and we see that n cubed is greater than, this is essentially n, so this will go to 0, which is not enough to show divergence, so therefore it's inconclusive. And we can probably go through the limit comparison test. Limit comparison test, if we look, the relationship between numerator and denominator is essentially n to n cubed, or rather 2 degrees higher than the numerator, since the square root of n squared is simply just n. So n over n cubed is, if we reduce that, that's the same thing as 1 over n squared. So if we're dividing by 1 over n squared, if we're comparing with 1 over n squared, we know 1 over n squared will converge. So if we can show a sub n plus a sub n divided by b sub n, and if the result of this gives us a real number, then we know that this series must also share the same characteristics in terms of convergence as 1 over n squared. So if we take this rule of sequence divided by 1 over n squared, that's the same thing as dividing by the reciprocal or multiplying by n squared. And if we see n squared times square root of n squared, this is essentially going to be the same degree as the denominator, so they have same matching degrees. We take the coefficients, which is 1, and that's less than 0, or sorry, 1 is a real number. So as long as the result of a limit comparison test is a real number, our series will converge. Okay, so here we have tan of 1 over n. If we compare this with 1 over n, for instance, limit comparison test, we know 1 over n will diverge. So if we can show that this expression will go to a real number, then that's enough to show that the series will converge. So tangent of 1 over n over 1 over n. 1 over n as n approaches infinity, that's the same thing. Well, as n approaches infinity, we know that these expressions will go to 0. So what if we simplify this process a little bit and make it tan of n over n, or tan of t over t as t approaches 0, since essentially that's the same thing what's happening. As n approaches infinity, this expression is going to 0, so why not just make it t approaching 0, tan t over t. So tan t over t, if we simplify this a little bit, going through trig properties, limit properties here, tangent of t over t is same thing as sine of t over cosine of t, and then we know that sine of t over t is equal to 1, and as t approaches 0, for 1 over cosine t will equal to 1. So this is enough to show that limit comparison test will stand. Since 1 over n diverges, which is the one that we're comparing with, then this series must also diverge. 24. cosine of n over 2 over n squared plus 4n. We know that cosine of n over 2 will oscillate between -1 and 1. So if we compare this with 1 over n squared, for instance, okay, we know that 1 over n squared will converge by the p-series. So if we do a direct comparison test, we know that 1 over n squared is greater than 1 over n squared plus 4n. We know that essentially cosine n over 2 is going to oscillate close to values, oscillate to values close to 1. So we know 1 over n squared is greater than equal to 1 over n squared plus 4n, and we know that this expression, or this rule of sequence, will converge. So anything that is less must also converge. So by direct comparison test, we know the series will converge. N factorial over e to the n squared. We see that this using ratio test will probably be the best fit. So we want to do a limit as n approaches infinity for a sub n plus 1 divided by a sub n. A sub n plus 1 is here, divided by a sub n. Divided by a sub n is the same thing as multiplied by the reciprocal. And if we try to clean this expression up here, n plus 1 factorial over n factorial is essentially n plus 1. And then here, e to the n plus 1 squared and e to the n squared. If I expand this exponent out, I get e to the n squared plus 2n plus 1. The e to the n squared essentially cancels out. We're left with n plus 1 over e to the 2n plus 1 as n approaches infinity. And here, if we go through comparative growth rates, we know that exponential function will grow at a faster rate than algebraic. So therefore, we know this expression will go to 0, and 0 is less than 1. So therefore, ratio test shows the series will converge. Okay, 26 here, n squared plus 1 over 5 to the n. If we go through nth term test, denominator will grow at a faster rate than the numerator. We know this expression will go to 0, so nth term test is inconclusive. We see exponential here, so let's go through ratio test. So we do the a sub n plus 1 divided by a sub n, same thing as multiplying by the reciprocal. And if we expand the numerator out here, we can simplify and reduce to be n squared plus 2n plus 2. 5 to the n will cancel out, leaving us with just 5. We see comparing the degrees are the same. So we take the coefficients, which is 1/5. 1/5 is less than 1. So we know the series will converge by ratio test. 27, k natural log of k over k plus 1 cubed. So let's do comparison test here. We know that k over k cubed is essentially 1 over k squared. And natural log of k, we can do something that is a little bit greater than natural log of k, which is square root of k. So square root of k over k squared is essentially 1 over k to the 3/2. So if we're comparing with 1 over k to the 3/2, we know that this will converge simply by power series. Since in this case 3/2 is greater than 1, that's enough for series to converge by p series. So we do a sub n divided by b sub n, which is the same thing as multiplied by the reciprocal. And if we reduce this a little bit more, we see that this will essentially be less than 1. And because of that, we know that the series must converge by the limit comparison test. Right? Or gives a real number that's less than 1. Here, e to the 1 over n squared. If we look at this relationship here, it looks like we can maybe go through integral test. So if we look at this, if we look at conditions that need to be met here, our function as n approaches infinity, this expression will always be positive, always continuous, as long as we're using n greater than 1. And then this value is always decreasing. Okay. And so if we go through integral test here, taking the integral of this expression, e to the 1 over x squared, and converting this to be in terms of x. If we let the u value be the exponent here, we can get that to find the derivative to make it match the x squared in the denominator. We're essentially taking the integral of e to the u, which is e to the u, and replace the u back in terms of 1 over x, and then plug in upper and lower bound. Upper bound gets plugged in, e to the 1 over b minus 1 over e. Limit as b approaches infinity. This will essentially go to 0, so e to the 0 is 1. 1 minus e is a real number. So since the result of integral of the improper integral of this expression will go to a real number, we know that the series must also converge. Okay. 29, the arc tangent of n. Arc tangent of n, we know that arctangent of n over n to the 3/2, that's essentially what happens here, n times square root of n. We know this expression. We know arctangent of n as n approaches infinity will approach pi over 2. And we know pi over 2 over n to the 3/2 is going to be greater than this expression. And since we know this is greater than arctangent, or greater than or equal to arctangent over n to the 3/2, we know this series will converge by the p-series. So we know this must be less than or equal to. So therefore, by direct comparison test, since pi over 2 over n to the 3/2 converges, our series must also converge.